In this video, we're going to discuss net ionic equations. Net ionic equations are important when we're talking about precipitation reactions. Net ionic equations only show the elements, compounds, and more importantly, the ions that are directly involved in the resulting chemical reaction. So an example of this is, say, if you add lead nitrate and potassium iodate to a beaker and they react, you see that these two ions here combine to form our solid product. So the net ionic equation for this would only show the things that are reacting, i.e. the lead and the iodate ion. It would not include the K and the NO3 because they do not change form and therefore do not participate in the reaction. So what this means is that the potassium and the nitrate ion, the K plus and the NO3 minus, are what we call spectator ions. These are ions that do not take part in the chemical reaction. And the way that you can oftentimes determine that is that the chemical on the reactant side is the same on the product side. So if you wrote out this whole equation here, plus iO3, everything split into ions, plus K plus NO3 minus, very long, okay. You'll find that you end up with K plus NO3 minus after the reaction has happened in PbIO3 solid. What you'll find here is that the potassium and the nitrate are in the same form on the reactant side and the product side, and therefore they do not chemically react. So that's what it means by saying that the ions found in the solution are the same before and after the reaction. So let's look at another example here really quickly before I ask you to do something like this on your own. So here's another one with lead nitrate with sodium iodide. This is our balanced molecular equation here. And we see that this, when we swap our cations here, like we learned to do, we end up with sodium nitrate and lead iodide. We would then go to our solubility chart in order to figure out what the solid is in our reactant side, and we see that the lead here is the solid, and this one is aqueous, aqueous, aqueous. Now, if something is aqueous, that means that it breaks apart into its ions in solution. So by using this, we can determine the total ionic equation. So the total ionic equation is where you write out all the ions, essentially. So we're going to do that here. We're going to split everything into ions. Pb2 plus NO3 minus, there's two of those, plus 2, Na plus 2I minus, because this 2 applies to both the sodium and the iodide. And then this is going to form our 2Na plus 2NO3. This 2 goes to both this and the polyatomic ion NO3. And then our PbI2 does not split into ions because it is a solid. So it does not ionize. Only aqueous ionizes. So only aqueous things will ionize, or again, ionize means turn into ions. So now that we have our total ionic equation, we can write our net ionic equation. And our net ionic equation, again, only includes the things that react. Only includes that react, i.e. it means you leave out your spectator ions. So let's go ahead and mark out our spectator ions so we can see this. So we've got nitrate on this side, sodium on this side, sodium on this side. So what's left is our Pb2+, plus 2I minus goes to PbI2. And that would be your net ionic equation. I'm going to write the states here as well. You should also write states for your net ionic equation so that we can see if it's aqueous or solid. Okay, so now it's your turn. There's a precipitate that forms whenever an aqueous solution of ammonium sulfate is mixed with barium nitrate. It asks you to write out the net ionic equation for this reaction. To make your life simpler, I am going to go ahead and write out the chemical formula for you here. It's NH4SO4. On an exam, this would not be the case. You'd be asked to know these polyatomic ions. You would need that. You are given a polyatomic ion chart as well, so you could look at your polyatomic ion chart to find their identities. This is a +1 and a 2-. So we're going to have NH4 here. Barium is a 2+, nitrate is a -1. So we're going to have an NO3 2. Okay, so it asks you to write out the net ionic equation for this reaction. In order to do that, you're going to need to predict the products, like we learned last time. And you're going to need your solubility chart. The solubility chart can be found on Canvas under this module for today. So if you want to pull up a separate one, you can. And that's going to be the best way to find this. I'll also put it in the Ed Puzzle question. Okay. All right, so determine the net ionic equation here. Remember that you need to split up things that are aqueous into ions, cancel out your spectator ions in order to find what is actually participating in the reaction in order to make your solid product. So let's look at the answer for this problem. In order to find our products, we need to swap our cations. So we're going to do so. NH4, NO3. These are 1 to 1, so we don't need any subscripts. Plus Ea, SO4. This is a 2+ and a 2-. Okay, let's go ahead and balance this as well, because in order to write our net ionic equation out, we're going to need it to be balanced too. So we have 2 NH4s here, so I'm going to go ahead and put a 2 here, and I think that balances the equation. So now we have 2 nitrates, everything else is good. So this is our balanced chemical equation. Now, in order to find our net ionic equation, we need to know what's aqueous and what's not. If you go to your solubility chart, you're going to find that things with ammonium are always soluble. Things with nitrate, always soluble. No exceptions. Anytime you see NH4+, it's going to be soluble. Anytime you see nitrate, NO3+, or NO3-, it's going to be soluble. So we definitely know these are aqueous. Using that same logic, we know that this one is also definitely aqueous because it's got both of your super duper aqueous polyatomic ions in it. And so that leaves us with this one as our solid, and you'll find this under the exceptions rule. So if you go down into the exceptions, it says sulfates are always soluble except for these few ions. Barium is one of those. So if we write out our net ionic equation, split everything into ions, you're going to see a couple of things cancel out. So if it's aqueous on one side, it's aqueous on the other, it's in the same form, then it can cancel out. So this cancels because they're both aqueous. Then we see that our nitrate also cancels because it is aqueous in both forms. Our barium and sulfate cannot because they are solids here. So if you wanted to write out your total ionic equation, you could. I'm going to skip straight to our net ionic equation. This is going to help save you time if you can get used to kind of doing it this way on exams as well. So we have SO4, 2-, aqueous, and Ba, 2+, aqueous. In our reactant side on the left, and on the product side, we have Ba, SO4, solid. This is our net ionic equation. Remember that your total ionic equation is where everything is split into ions. You won't be asked that most of the time. You'll usually be asked for this one. But don't get them mixed up. So let's take a look at why some of these ionic compounds that we've looked at dissolve in water and others don't, right? You have your solubility chart. Some of them dissolve, some of them don't. So this is what salts look like when they are a crystal. So our ionic compounds come in crystal structures, and the ions are all tightly packed together. So if this was sodium, we'd have NaCl, NaCl. And in order for these things to dissolve, say like in water, you have to break them physically apart. They have to come apart. So last time we had talked about solubility of molecular compounds like CO2 in water, that sort of thing. These are very different because they don't come in these crystal structures. So ionic compounds are often in these crystal structures. We also call this a lattice, a crystal lattice. That makes sense if you think about like salt in your kitchen. We have salt crystals, right? That's kind of what these things look like. So in order for your salt crystals to break apart into water, we have to have this process where the water balances the charges when they're liberated from the crystalline lattice. So remember that water is very, very polar, right? We learned this last time. It's really, really polar. It pulls really hard this way. It's almost an ionic compound itself. It's so super duper polar, which is why it can separate these compounds. So what has to happen is this bond right here between the NaCl, or the attraction between the NaCl, sorry, it's not a bond, but the attraction between the positive and the negative charge of the NaCl must be broken by the water molecules. So this one is broken, and we see this new ion dipole form here, which is a type of attraction between the ions and the polar water molecules. So you can see here that the partial positive end of the water, the hydrogen part, lines up to the negative charge of the chlorine. If we look at our sodium atoms here, you'll see that the water's flipped. So the partial negative of our water, the oxygens, is pointing towards the positive. And so it kind of like balances out the charges. So you'll see that the positive ions are surrounded by the partial negatives of the water, and the negatives of our ions are surrounded by the partial positive sides of the water. And that this attraction is pretty strong. So we've got to break the attraction between the sodium and chloride and create a favorable attraction between the water and the individual ions. And when that happens, we call our salt dissolved. So whenever all of the little ions are pulled apart by the water molecules, that's what we call dissolution, or we consider it being dissolved. So this brings up our original question. What determines whether or not a salt separates in water? Why does sodium chloride break apart, but then like our barium sulfate doesn't? It has to do with the attraction force between your ions. So between Na and Cl, this force right here, there's going to be a difference between that force versus a difference between this force. So the question is the attraction between the salt ions stronger, or is the attraction between the salt and the water stronger? So water is really polar. Again, it's almost an ion itself. There's more water molecules than there are your salt ions. So there's a lot of things at play here. This is kind of our what we call an ion dipole force here, where the ion is interacting with the water molecule. You can see it in a bigger picture here where we have more water surrounding an ion. So that's the name of this force here. So kind of here's what's going on whenever these salt crystals are being dissolved. So this is a precipitate. You can see this is something not dissolving, whereas your NaCl, like he was pouring into the liquid, you can see that the water surrounds the salt crystals and pulls them apart. Whereas precipitates don't do that. The water's there, but it doesn't separate it. So the water wouldn't be able to get in there like it's doing for these. And that's what causes a precipitate. So I wanted to take a little bit of time to talk about water. So if you notice here, water is a very unique material. Water dissolves a lot of ions. It's the basis of life. It does a lot of really weird things. So we're going to use water as a model in order to segue into our next topic on intermolecular force, forces between molecules. So water does a couple of interesting things. So we had learned in topic 1, we had learned about density. We had learned that as something is a gas, it's less dense, the molecules are further apart. As it goes to a liquid, the molecules get closer together. As it goes to a solid, the molecules get even closer together, and they're very, very dense at a solid. But water is really funky. So water switches the liquid and the solid phase. So it's more dense as a liquid than it is as a solid. It's less dense as a solid. This is a very unique property that only water exhibits. Very other few molecules do this. And this is why things explode whenever they freeze, right? Like if you've ever put a water bottle, a closed water bottle in the freezer, it'll actually explode because ice expands when it freezes. Very few other molecules do this. Another thing that's unique about water is that it's a liquid at room temperature. That's really strange for something that is the molecular weight of water. So water has a molecular weight of 18.02 grams per mole. Everything else on the periodic table that has this weight, so like this gas here, this H2S gas is 34.1 grams per mole. It's a gas, but this one's a liquid. Something's going on really weird here. Our NH3 has a mass of 17.03 grams per mole. It's a gas too. So water has a very unique property that lets it do this. Another thing that you're going to see with water is that it has a really high boiling point, which lets it hold a lot of heat. So water, if you want to turn it from a liquid into a gas, we know that its boiling point is 100 degrees Celsius. This similar molecular compound that we looked at, this H2S, is 34.01 grams per mole. This is 18.02 grams per mole. It has a boiling point of minus 60. It's got to be like this cold outside, and it will still boil, even if it's at that temperature. So most things that are the molecular weight of water have a really low boiling point. They are normally gases, and water doesn't do this, which lets it absorb a lot of heat in the earth without evaporating. So it's really, really good for moderating Earth's temperature. And this is explained, again, by attractive forces between the molecules. The last property that we saw in this topic is that water dissolves a large variety of chemicals. It does this because it's extremely polar, it's nearly ionic, which lets it stabilize ions using this ion dipole force. So that's a very unique property of water. Things like H2S will not do that. They will not dissolve salts because they don't have this strong ion dipole force because they aren't as polar. So here are the few things that makes water unique that we just discussed. It's a liquid at room temperature. It's got a high boiling point. It expands when it forms a solid. And it has an ability to dissolve a large variety of chemical substances. So make sure you know these, because when we talk about forces in the next topic, we're going to examine all of the reasons why this occurs. So I want you to think for a minute about what causes water to be a liquid at room temperature. why would, say, if you have another water molecule here, you have another H2. I'm always using H2S because it's so similar to water. Really, really similar, but it acts so differently. So what causes water to be a liquid at room temperature? Why would this one here, why would this one be more dense? More dense, less dense. What are some reasons you can think of that this might happen? So what's going on here is that between these water molecules and these H2S molecules, there's something holding them together. There's a force that holds them together. And this force is very different between these two molecules. And we're going to discuss why. So this force here is really, really strong. And that means that it is more compact. So we see this pulling. So this is more negative and positive. And so because positives and negatives, the difference is bigger, they're pulling more tightly on each other. And this one has a weak force. So what happens with that weak force is that they can be further apart and they're happier there. So we had learned last time about different magnitudes of polarity. We had drawn our dipole arrows on our molecules. You can see here that for HF we have a really big dipole moment. For HBr we have a much smaller dipole moment because this is the most electronegative atom on the periodic table. So this has a giant dipole moment here. And it has it's very, very polar. So because of these differences in polarities, we can actually name the differences in polarities. So on our compounds, if we have something that has different electronegativity differences here, if you have something that's really high, like we saw in the last one, it's considered an ionic compound because it has an ionic bond. If your polarity difference is in this range, it's what we consider polar covalent. If it's in this range, it's what we consider non-polar covalent. This is the name of the chemical bonds in between the atoms in a molecule or an ionic compound, a molecular or an ionic compound. So we can look here at H and Cl, H, F, lithium, and chloride. Let's look at all of these examples. So our hydrogen is 2.1, our chloride is 3.0. This difference here is 0.9, which means that it falls in our polar covalent category. So this bond right here is a polar covalent bond. That also tells us that this is a molecular compound. So anything in these two ranges here are molecular compounds. Anything here is an ionic compound. So a lot of you had asked me, I think it was like topic 2 when we were naming things. You said like, what about the metalloids, right? Like in this area right here, these are metalloids. Like how do we know if it's an ionic compound or molecular compound? This is the answer to that. So if you see that there's an electronegativity difference that falls in this molecular compound range, it's a molecular compound. If you see an electronegativity difference here in the ionic compound area, it's got ionic character. It has an ionic bond. And that's literally the only way we can tell. So our HF here, 2.1 versus our fluorine, I think it's like 3.9, but we'll use 4.0. Okay, so sorry, this is actually not ionic. It's super duper close to being ionic. It's like the closest you can actually get. It's 1.9. So this is technically polar covalent. But it's really, really close to being ionic. You can see the same thing happening with water. H and O, we've got 2.1. This is at 3.5. So your difference here is 1.4. So even though it's polar covalent, it's very close to being ionic. Lithium chloride, let's examine lithium chloride. So lithium is here, it's 1.0, minus our chloride, which is 3.0. That gives us a difference of 2. So that's definitely an ionic bond, which means that electrons are not shared here. Remember that the distinction is electrons are shared with these. And electrons are not shared for these. So that's how we tell if something is ionic or polar or nonpolar. This is the different type of bonds in between these. This is what we call intramolecular force. This is a very important term, so please make sure you write it down. So intramolecular forces is the force present inside of a molecule, in between an atom and another atom. So it's related to the magnitude of the dipole moment. So remember that if something's nonpolar covalent, we are sharing electrons, and they are shared almost evenly. If something is polar covalent, electrons are shared, yes, but often more towards one atom than the other one. If it's an ionic bond, then we don't see sharing of electrons, we see a stealing of electrons. All of the electrons go to one atom entirely, and they're removed from the other one. And so intramolecular force is something here that holds these together. And it does this in the form of different types of bonds. So in this case, this is a polar covalent bond. In other cases, we might have an ionic bond. We usually write it like this. This is an ionic bond. Or we might have a nonpolar covalent bond, which might happen between something that has really low electronegativity. This would be polar covalent, non-polar covalent, because there's no polarity difference there. Something else that I did want to point out is that, I forgot to mention this. So you see that it says 1.6 and 2.0 here. There's actually a little bit of a difference in between here. So this 1.6 to 2.0 range can be either ionic or molecular. The only way to know here is if a metal is involved in the chemical bond or not. So in the case of HF, it falls to 1.9, which means it's in this range. This here is a nonmetal with a nonmetal, meaning that it's going to be a polar covalent. If you had a metal with a nonmetal, then it would qualify as ionic if it was in this range. Okay, so now it's your turn. Use a Pauling scale to determine the intermolecular force between the following molecules here, KCl and H2S. Remember that anything that has a electronegativity difference of 0 to 0.5 is what we consider nonpolar covalent. 0.5 to 1.6 is polar covalent, and 2 or higher is ionic. All right, so let's take a look at how to solve this one. So if we go to our Pauling scale, we'll see that our potassium is at 0.8, our chlorine is at 3.0. So if we take this difference here, we find that we end up with 2.2. So this means that this is ionic. This is an ionic bond. H2S, we've got 2.1 for our hydrogen, 2.5 for our sulfur, which means it's 0.4, which means that this is a non-polar covalent bond. Now keep in mind that molecules can have more than one type of intramolecular force. So the same way that we can have different types of dipole moments inside of a molecule, we can name these different things. So for example, this hydrogen peroxide molecule here, we've got this going on and this going on, and then we've got a nonpolar bond here because we've got an electronegativity difference of 0. And then these here are polar covalent. So you can have more than one type of bond inside each of a molecule. So we had looked at water and had asked what causes water to be a liquid at room temperature. Well, we can see the difference in these types of bonds and see this difference here. So this is our ionic bond here with lithium chloride, and we can see it's normally a solid. If we look here at acetone, acetone is normally a liquid, and it's got a polar covalent bond here. It also has some nonpolar covalent bonds here. But because of the polar covalent, that makes it a liquid. Our nonpolar covalent compounds, like some of these molecules here, fluorine bonded to fluorine, are usually gases. So water is often a liquid because it's got a polar covalent bond. So we'll talk in the next topic a little bit more about these interesting properties of water and the other types of forces that cause it to exhibit the properties that it does.